So, okay, so we will start with the, or rather, we will continue with the previous topic, that is the design of Aerator. And in the yesterday's class, we have covered the design of inclined slab and the design of channels. Okay. Now the only part which is remaining, that is the central shaft. Okay. So you can see the picture which is there on the right hand side. This is a central shaft, and the basic purpose of central shaft is to provide the water to the aerator. Okay, so this central shaft is basically a cylinder kind of a structure which is completely filled with the water, right? So the height of this cylinder is given to you, this central shaft is given to you, that is 2 meters. And if you remember, we have taken the external diameter of this central shaft as 900 millimeters, okay, zero point 0.9 meters, roughly 1 meter, right? So we will continue with the design part, and for the design purpose, we have to first of all assume the thickness of the central shaft. So let us assume the thickness of the central shaft as 150 millimeters. Okay. So if you consider the diameter as 150 millimeters, or the thickness as 150 millimeter, the clear diameter will become 600 mm. Okay, because the thickness has to be deducted from both the sides, so the clear diameter is going to become 600 mm. Now, if you remember, while designing the GSR, we have designed the wall, and we have designed the wall for bending as well as axial tension as well as for base shear. So this particular structure is exactly similar to that one, isn't it? It's a circular tank kind of a structure, isn't it? But the problem here is h square by dt value, right? So your h square by dt value earlier, if you remember in the design of GSR, we used to refer IS 3370 part 4, isn't it? 1964 for the design tables. And depending on the h square by dt value, we are referring different tables, table number 8, table number 9, table number 10, and accordingly we are going to take the coefficients for that. Okay. But if you see the h square by dt value for this particular structure, so in this case, the h square value here, the height value will be something like 2 square, okay, and the innermost diameter will be 0.6, and the thickness will be 0.15. Okay, so can somebody tell me how much will be the value of this? Sorry, 44.44. Okay, but now the issue is when you refer IS code 3370 part 4. So let me open IS code for you. If you have copies of IS code, please open the IS code. Okay, so this is the IS code. We will be referring to different tables. Okay, let me slightly go down. So I have to go to, yes. Yes, please come in. Uh, yes. So let us see if we are going for table number 9. So the table number 9 shows the coefficients for tension in circular cylindrical wall with fixed base and free at top. This is what we have already referred. Okay, but if you see the values of h square by dt, so the limit is 0.4 to 16. Okay, but what we have got, that is h square by dt value, we have just now seen, we are getting the h square by dt value as 44.44. So there is a limitation that this particular table which is given in the IS code, it is applicable only for h square by values which is in the range of 0.4 to 16. Okay. So now in this particular case, what has to be done? Right. So traditionally, if we go, what we can do is we can calculate what will be the water pressure at the base, because the vertical cylindrical shaft will be subjected to lateral loading, which will be a triangular loading. This is only due to the water. Okay, so this water pressure P, which is over here at the base, it can be calculated by a simple expression H is H into gamma W, where this H value, okay, so height value will be 2, gamma W will be 10. So the pressure which is coming at the base is 20 kilonewton per meter square. Okay, so now this is the pressure which is coming at the base. This is the maximum pressure. So we can calculate the hook tension. Hook tension is simply pressure into d by 2, or rather pressure into r, right? So the pressure value is basically 20, and r value, just now we have seen the innermost radius, clear radius, or the diameter is 600, so radius will be 300 mm, so this will be 0.3. Okay, so how much will be this one? How much will be this one? That is zero point 0.3 into 20, that is 6 kilonewton. Okay, so the tension which is there in the wall, so maximum tension will be there at the bottom, and the maximum tension is 6 kilonewton. This is the axial tension. Okay, so now if you want to provide the AST, because concrete is weak in tension, so we have to provide the steel to resist the tension, right? So the simple expression is AST is hoop tension divided by sigma ST. So this is 6 kilonewton, that is 6 into 10 to the power 3. Sigma ST will be your 130. Okay, how much will be this one? Can someone tell me, please? Sorry, 46.1. This is millimeter square. Okay, so you see the value of hoop tension is very less. Because of this, the steel which is required to resist the tension, it is also very less. Okay, but also we have to take care of AST minimum. So AST minimum is 0.24% of the cross section area. The thickness we have assumed over here is 150. So here the value will be something like 0.24 divided by 100 into 150 into 1000. How much is this? I think 360. Okay, so maximum value is 360 millimeter square. Correct? So how much spacing is required? So if you provide 8 dia at the rate for 360 square, कितना आना चाहिए? 130. So we can provide 125. 139 is the spacing. So we have to reduce on the lower side. So we can take 125. है ना? 125 center to center. This time we are not providing 150 because the thickness of the section is 150 Okay, it should not be less than 150 so 125 is sufficient. Sorry. So I'm sure if you calculate the actual tensile stress, definitely it will be less than the permissible tensile stress in concrete under direct tension. But still, as a part of design process, you have to do this. So maximum hoop tension is 6 into 10 to the power 3. So area of the concrete is 150 into 1000. What is the M value? Someone please tell me the value of M. M कितना है? 10.98. Okay, and how much is the AST? That is 8 dia bars at 125 center to center. कितना आता है? 8 dia bars at 125 center to center. How much is this steel? That is 402 square. ठीक है, तो ये AST आ गया आपका 402. How much is this stress now? टेंसिल स्ट्रेस कितना आ रहा है? 0.04, वेरी लेस है ना, 0.04. So you can see it is well within the permissible limit of permissible tensile stress. Okay. Now coming to the bending moment. Now here you see as such bending moment will not be there in this particular uh, central shaft. Why? Because you see it is having the fixed at the base, and at the top also you will find the structure is completely surrounded by the inclined wall. Okay, so as such there won't be any bending. Okay, because every time it is supported at the top as well as at the bottom. So what we are doing is, since it is everything is almost fixed, so we are calculating it, we are going for the nominal bending moment. So nominal bending moment, generally we take height of the water multiplied by density of the water. Just that's it, nothing much. So height of the water is basically 2 and density of water is 10. So the nominal bending moment will be 20 kilonewton meter. Okay, so this is a nominal bending moment, right? Now coming to the self weight of the wall, because we have to check the axial stress and the bending stress, and we have to check the combined effect also. So the self weight of the wall, so self weight of the wall, if you see from the top, we have outer radius, we have inner radius. So in between whatever area is there, that area I am going to calculate. So here the self weight of the wall, so outer radius is 0.45, because the diameter, if you see, it is 900 mm, and the inner radius is basically 0. I think 3. Okay, because inner diameter is 600 multiplied by, so height of the water, so height of the water is basically sorry, height of the wall, not water, height of the wall is basically 2 meters, and density of the concrete is 25. How much is the self weight? कितना आ रहा है? 17 point. This is in kilonewton. Okay. So the direct stress will be something like 17.67 into 10 to the power 3. This area is basically pi r outer square minus r inner square. So this will be 0.45 square minus 0.3 square. Okay. How much is direct stress? हाँ बोलो, anyone? Direct stress in the concrete? 0.05. 0.05, very less, isn't it? Newtons per millimeter square. बराबर है? Someone please cross check. Okay. Now coming to the bending stress. So bending stress is m by I into y. Okay. Bending moment, we have already calculated this value as 20. Then it will be 10 to the power 6. Okay, because I am converting this into a newtons and mm. Is it okay? Fine. And I by y. So moment of inertia. What will be the moment of inertia? Pi by 64 into d to the power 4. This is for the circle, but we have two circles. One is outer and one is the inner one. Okay, so your I value, so I am writing down over here. So your I value will be pi by 64 into d outer square. So d outer is 900 not square to the power 4, and inner will be 600 to the power 4. So this value will go over here, and the value of y will be 900 divided by 2, that is 450 m. Okay, so please calculate the bending stress. Sorry. Anybody else? Please cross check. 0.348 millimeter square. Then we have to go for the combined effect of actual stresses. So sigma c actual, this value we have calculated as 0.05, which is very less. Bending stress is 0.348. I am 100% sure this value will be very, very less. नारा combined stress. बोलो. क्या कैलकुलेट कर रहे हो यार इतनी देर से? 0.05. ठीक है, so you see it is very, very less. Okay, now about the reinforcement. So you see we have to provide the reinforcement which is shown in this particular figure. And if you remember, we have calculated the AST earlier, and this AST we have provided AST minimum actually rather. So this AST minimum we have provided 8 mm dia bars at 25 mm center to center. So the same AST has to be provided in vertical direction as well as in the circumferential direction. Okay, so both, that is this one as well as this one. Okay, so this is 8 mm dia at 125 center to center. Okay, here you need to remember one thing. We have to provide the reinforcement on both the sides if the thickness is greater. Okay, this we have already seen in the design of GSR, especially the cylindrical wall. Okay, so same rules are applicable over here, but since the thickness is less, so we can provide the AST in this particular fashion. Okay, and please do mention the thickness also. Here the thickness is 150 mm. Okay, so please mention that one also. Okay, so are there any queries? Fine. So we will quickly go through the design of foundation. Foundation is pretty simple. So it's a simple circular foundation. Okay, and the basic rule of the foundation is whatever is the thickness of the wall, we have to provide the thickness of the foundation greater than that. Okay, this also we have seen in the design of GSR. So since the thickness of the wall is 150 mm, so we are going for the thickness of the foundation as 200 millimeters. This is what we are assuming, right? Apart from this, we are assuming the projection. So I'm talking about this projection. So this projection, I'm assuming this as 100 mm, 4-inch standard, right? And I am assuming, or rather I am designing this particular foundation for SBC of 100 kilonewton per meter square. So this value will be given to you. In actual practice, you have to investigate the soil, and whatever is the SBC, accordingly we have to take the values. Okay, so the very first thing is we have to calculate the load. Okay, the first thing, the first load is the self weight of the shaft wall. So this load we have already calculated over here in the second line. If you see, we have calculated the load of the wall as 17.67 kilonewton, isn't it? So 17.67. So I'm just writing down over here, this is 17.67 kilonewton. Okay, then we have to find out how much is the weight of the water which is inside that particular shaft. Okay, so basically we have to calculate the volume multiplied by density. So volume is nothing but area into height, so pi r inner square into height of the water. So this is going to give you a volume multiplied by density. Okay, so r inner square, so r inner is 0.3, height of the water is 2, density of water is 10. How much is the weight of the water? Can someone tell me? Yes, 5.65 kilonewton. Okay, then the self weight of the footing. So again, it's a circular footing, right? So cross section area, if you see, it is a simple circle. So area of the circle multiplied by height of the footing, so it is going to give you volume, and volume multiplied by density of the concrete. Okay, so pi by 4 d outer. So d outer, if you see, this is the value of d. It inclusive of 600 inner, then 150 this side, 150 this side. So this will be 900. Okay, 900, 900 plus 100 this side plus 100 this side, that is 1100. Okay, so this is 1.1 square. Depth of the foundation, I am assuming this as 200. Okay, or rather you can take zero point 0.2. Density of the concrete is 25. How much is this? Sorry, 4.7. That's it, kilonewtons. Okay, so on the foundation we have the self weight of the wall plus the water plus the self weight of the foundation. So the total, that is 17.67, 5.64 and 4.7. How much is the total load? कितना आ रहा है? Sorry, 20 kilo Newton. Okay, so this is 28.07 kilonewton, and the area. Okay, so this area is pi by 4 into d square. D is 1.1 square. बराबर है? Okay, how much is this? कितना आ रहा है? 28.07, that is in kilonewtons, and pi by 4 into 1.1 square. कितना आ रहा है? 20 29.5. This is kilonewton per meter square, and this SBC value is 100. Okay, so definitely everything looks good. Okay, now as far as AST is concerned, because it is supporting a simple tower and not much bending moments or shear force or any kind of loads are there, values are very less. So what we can do is we can provide the minimum AST Okay, so AST can be calculated as 0.24% of cross section area. So this is 200 into 1000. So this comes out to be something like 480 millimeter square. Okay, so how much will be the spacing of 10 dia bars? 10 का spacing कितना आएगा? Sorry, 153. So we can go with 150 center to center. Is it so? बराबर है? Okay, so we have to provide reinforcement. If you see from the top, it should be provided in form of a grid. Okay, otherwise, if the dimensions are more, you can provide in a radial fashion. Okay, both way it is acceptable, and the reinforcement has to be provided at the top. Okay, because there is a possibility of hogging, because centrally there will be a pressure and there is a possibility of hogging. Okay, I hope this is clear to everybody. Are there any queries? Online students, are there any queries?
No, sir.
Okay, fine. So this completes the aerator. We will quickly take another design. Okay, please finish this fast. Okay, shall I continue? So now we will start with another topic. It's a very small design. There are only 9 slides. Okay, all right. So we'll start with the design of flash mixer. So what happens is the water is taken from the source, then it goes intake well is there. Okay, that is jack well pump house. Then the screening is done, then aeration is done, then there is a coagulation tank. Okay, so in coagulation tank what happens, the coagulant is added in the water, and the basic purpose of coagulant is what, anybody? It reacts with the suspended particles and it starts formation of flocks. Okay, so this coagulant tank is basically a simple tank. Okay, nothing much is there. It can be of circular shape, it can be of square shape, it can be of even a rectangular shape. Okay, the basic purpose is when the coagulant is added, it should be mixed properly. Okay, so there are different types of coagulation tanks are available. Okay, the very first and very common type of coagulation tank is mechanical coagulation tank. So here, if you see the picture which is there at the bottom, so here you can see there is a coagulant feed which is there in the bottom. Okay, so here you can see this is your coagulation feed. So coagulant is feeded and it will come over here, and there is a mechanical mixer over here. There are blades which are there which are continuously rotating, and because of this the coagulant is properly added in the water, and once the coagulant is added it will be transported for the next unit. Okay, this is a very simple basic available funda, right? If you visit the Gorewada water treatment plant, which is just very near to our college, there you will find they have just created a simple tank, and once the water aeration is done, then it's a deep tank actually. So water will fall from a greater height, probably 2 or 3 meters. So because of this greater height, what will happen? Turbulence will be there. Okay, and in that turbulence itself, they are adding the coagulant. Okay, so this is a simple process. There is no mechanical device which is installed over there to mix the coagulant with the water. Okay, but anyway, the process is very simple. All we have to do is just we have to design a simple tank. That's it. Okay, so we will just quickly go through the design process. So let us assume that we have to design a circular flash mixer which is having height of 4 meter. So 4 meter is very big height. Okay, almost the height of this room. Okay, so this is 4 meter height and it has got a diameter of 2 meters, and this is a mechanical one. Okay, it is not the gravity one, it's a mechanical one. So if you use these dimensions, let us assume the thickness of this wall as 150 mm, and again the issue is same, since this is circular kind of a structure, and if you go for h square by dt value, so this is 4 square, diameter is 2 and thickness is 0.15. How much is this h square by dt value? Someone please tell me. 53. Okay, okay, so the range is not available again, है ना? So since the range is not available, what we have to do, we have to go in the traditional way. So we are going to calculate the pressure which is there at the bottom. So pressure at the bottom can be calculated height into density of water. So height is basically 4 meters, density of water is 10. So this is going to give me 40 kilonewton per meter square of pressure which is acting at the base. And as you move from base to the top, the pressure is going to get reduced. So for the maximum pressure, we are going to calculate the hoop tension. So hoop tension is P into dy 2 or P into R. So P is 40, okay, and R is the radius. So diameter is 2, so radius will be 1. Okay, so this is going to give me 40 kilonewton hoop tension, which is very high. Okay, so accordingly now we have to go for the AST calculation. So this is 40 into 10 raised to power 3, whereas sigma st is 130. Okay, how much is this? Anybody? And you can also calculate this 0.2524% of cross section area with 150 thickness, it comes out to be 360. Okay, कितना आ रहा? 40 into 10 to the power 3 divided by 130. 308. Okay, so maximum is 360 mm square. So what we can do, we can provide 8 mm dia at 125, I suppose, है ना? At 125 center to center. Okay, again you have to check the stresses. So this is 40 into 10 to the power 3. ये आ रहा था कुछ, कितना आ रहा था? 8 mm dia at 125 center to center कितना आ रहा था? AST 4 402. Okay, M is 10.98, I suppose, and this is 402. ये कितना आ रहा है? Zero 0.26, very less value. Okay, and I hope you know what to do if the values are not within the permissible limit. क्या करना चाहिए? या तो थिकनेस बढ़ा या तो स्टील बढ़ा, ठीक है, बट दीज आर वेरी स्मॉल स्ट्रक्चर्स. ओके, सो डोंट हैव टू वरी अबाउट दिस. ओके, फाइन, चलो कंटिन्यू. लिखो, जल्दी जल्दी लिखो. ठीक है. I'm not covering the foundation for this. It will be a basic foundation, so it's a repetition. That's why I'm skipping this. Okay. Then coming to the another type, this is a square type of a you can say flash mixer. Okay. So basic thing is it is having a similar kind of a mechanism. Only thing is the shape is changed. So we have one we have one coagulant feed over here. So water will come like this. It will go down. It will go down, and here the water will be the coagulant will be added, and here there is a mixer. There is a blade. There is a blade. So the water is getting mixed, and the uh, outlet will be over here. Only thing is the shape is now changed. So you can see this side we have inlet. Okay, so यहाँ से पानी नीचे जाएगा, and here the water will come, and from here the water will go out. Okay, so we are we are going for the similar dimensions which we have assumed earlier. So earlier we have assumed the height as 4 meter. Here also I am assuming the height as 4 meter. In the previous one we have assumed the diameter as 2 meters. Okay, here I am assuming the square shape which is having 2 meter by 2 meter. Okay, and here the thickness we have to assume slightly more. Okay, why? I'll tell you. Because you see, the shape is going to make a lot of difference as far as the behavior is concerned. Because in the square shape there will be a proper bending, and in circular shape there is no actual bending, there is a hook tension. Okay, and for hook tension only steel is required. Here bending also steel is required, but the magnitude of bending moment which is generated in the square shape or even in the rectangular shape, it is on the higher side. That's why you will find most of the time circular shapes are preferred over the rectangular shapes. Okay, that we will see. Because you see most of the parameters are same. After the design of the square flash mixer, you will find the amount of steel and amount of concrete which is required is on the higher side as compared to the circular one. Okay, anyway, so you can see that picture. It's a square kind of a flash mixer, and you can even see the mechanical flash mixers blades are also there in that particular picture. Okay, so let us quickly go through the design. So here what is going to happen, that this is a square kind of a shape. So you can find if you take a simply supported beam, okay, or rather continuous beam, so you will get negative moment bending moment over the support. So this is exactly similar to this one. Okay, so you will find the negative bending moment will be there just above this one. Okay, here there will be negative moment, here there will be negative moment, and here there will be a positive bending moment. Okay, so the pressure will be there maximum at the bottom, of course. So this pressure value is nothing but the height of water multiplied by density of water. So height of the water is 4, density of water is 10. So the pressure at the base is 40 kilonewton per meter square. Okay, so this is very much similar to a situation where we have a simply supported beam, or rather continuous beam, where this pressure of 40 kilonewton per meter square is applied, isn't it? So for this the maximum bending moment will be wl square by 12, isn't it? So here the value of this w will be 40, into length will be 2 square, because the length of each span is 2 divided by 12. So can anybody tell me how much is the bending moment value? 13.13 na, not 30. 13 point, this is kilonewton meter. Okay, so for this much bending moment, first of all we need to see how much is the thickness which is required. Okay, so mr equals to qbd square. So your value will be something like 13.33 into 10 to the power 6. What will be the q value? 1.527. B value will be 1000. D value we have to calculate. How much is the D? बोलो. सॉरी, कितना रहा? 93.4. ओके, सो 93.4 प्लस क्लियर कवर, इफेक्टिव कवर, ये सब पकड़ के भी कितना जाएगा? ये कैपिटल डी कितना जाएगा? 150 से लेस ही जाएगा, है ना? सो व्हाट वी आर डूइंग इज वी आर एज्यूमिंग दिस एज 150 mm. So here this will be 150 mm and this will be now 125 mm. Okay, so amount of steel which is required. So bending moment, we have just now seen the bending moment is 13.33 into 10 to the power 6. Sigma st is 130, j is कितना था? 0.86 and d is 125. How much is this ast? 9, बहुत ज्यादा है ना? ठीक है, so now you see the difference. When we are going for the circular type of tank, the ast required was only 360. We have provided minimum ast, but now if you change the shape, the things are completely different and you require almost 3 times of the ast, right? 953 mm square. Okay, so can anybody tell me what will be the spacing of 12 mm dia bars? Yes, so this is 12 dia at 118 center to center. Okay, so 118 की जगह पे हम लोग क्या करेंगे? 100. Okay, so in place of 100, 118 we'll go for 100 center to center. Okay, as far as the vertical reinforcement is there, vertical reinforcement should be considered as the minimum one, ast minimum, that is this one. So we can provide 8 dia at 125 center to center. ठीक है, ast minimum is 360 and if you see the previous slides you will find 125 spacing is sufficient. Is it okay? This is what we have assumed. Earlier we have assumed this, okay, but if you see, this is what we have assumed, but when we have calculated, we thought that 150 is sufficient. Okay, but if you take d value as 250, it is beneficial. Why? Because your effective depth will be more. Here you can see in the ast calculation, the effective depth is 125. So if you take 250 as a thickness, so your effective depth will be something like 225, and accordingly your amount of steel will be reduced significantly because the d value is in the denominator. Okay, fine. But in any way your square shape is not at all recommended as far as the quantity of steel which is required is concerned. Square, a circular shape is more recommended because it is very safe, only tension is there and steel is provided. Okay, anyway, we have to check the bending stress also. Okay, so bending stress is bending moment. So bending moment value, I think it is 13.33 into 10 raised to power 6. I is BD cube by 12. So B will be 1000. Now D, your D value is, effective depth is 125, right? 125 cube divided by 12 and the distance of the farthest fiber. So the thickness is 150. So this will be 75. How much is the bending stress? कितना आ रहा है? Sorry, 6 point newtons per mm square. This should be less than sigma CBC. It's 8.5 newton per mm square. Okay, so this is safe, but still if you see the bending stress, it is very much closer to the actual or the permissible stress in concrete in bending. Okay, so even after providing this much of steel, this much of concrete, you see it is safe, but the quantity required, it is on the higher side. Okay, that's why the circular shape is more recommended, but in some cases circular shape is not possible. In that case we have to go for the square only, because square and rectangular, they are very easy for construction. Special formwork is required for circular tanks, whereas for square tanks as such no special formwork is needed. Okay, सो इसका भी मैं फाउंडेशन नहीं ले रहा हूँ. इट्स अ बेसिक फाउंडेशन, नॉट मच टू डिज़ाइन, एंड rest is pretty simple as far as this portion is concerned. Okay, so we will stop now and we will continue in the next class. Okay, let me quickly take your attendance.